We are going to look at the ideal gas law in homework packet 8, page 11, and then you'll be able to do some problems on page 12 with that. I'm going to go to a screen share here and find the document. I'm finding page 11. Put a couple of notes up here on this, and I'm just going to grab a little marker to annotate with. And it talks about Avogadro's hypothesis, where it says equal volumes of different gases at the same temperature and pressure contain the same number of molecules or same number of particles. Okay, there's a couple things going on here. If we're at standard temperature pressure, which is 0 degrees Celsius, 1 atmosphere pressure, 1 mole of gas is 22.4 liters. Okay, let's say I have only 0.15 moles of gas. Then I'm going to have a fraction of 22.4. I just take 0.15 times 22.4, and I get 3.4 liters. Now, why does this work that all gases are essentially behaving the same? We know gases are far apart. So the assumption is all gases behave the same, and they approximate what we call an ideal gas because there's no attractive or repulsive forces between the molecules. Why? Because they're so far apart. Okay, now let's say you lower the temperature and the gas approaches a liquid, or raise the pressure and the gas approaches a liquid. Then the ideal gas law doesn't work so well. But under most conditions, the ideal gas law works well as a model, probably 99+% accurate in the cases we use it for. So here we go. This is the ideal gas law, PV equals nRT. And let's look at the different terms that we have. We have P for pressure, V for volume, N for the number of moles of gas, T for temperature, and then R is the ideal gas constant that links things together. Okay, and the ideal gas constant is, I think we had C, it was a constant for the speed of light. We also had Planck's constant, which link things together when we were talking about energy and frequency. Pi is a constant that's used when you're finding areas or circumferences of circles. So it just so happens that R has certain values. One value is 0.0821 liter atmospheres per mole K. And take a look at the units because it will link things together. If I multiplied that number by 760, it would be liters millimeters mercury per mole K because there's 760 millimeters mercury in 1 atmosphere. These are the most common ones that we'll use for the gas law constant R. And then you got to use the one appropriate to the situation that you're in. So we're going to look at PV and T, which we've looked at before. R is this new constant. And now we're applying this concept where the number of moles affects things inside of a gas. And that makes sense. If you have more molecules of gas, that's going to affect, let's say, the pressure, all other things being equal, and so on, or the volume or something. Okay, let's go to the example on the bottom of page 11. It says, just go back here a little bit. I think this will be good. And it says, what pressure in atmosphere is exerted by 0.0325 moles of hydrogen gas in a 4.0 liter container at 35 degrees Celsius? So as I get used to working with this, I just pulled all these terms out to the side, and I'm trying to find the pressure. Okay, and it says in atmosphere, so I'm going to put a question mark there. Let's see, volume is 4.08 liters. The moles of gas is 0.325. Notice my R value, because the pressure is being found in atmospheres, I'm going to write 0.0821, and I write the liters atmospheres per mole K just to make sure my units are matching up. So example, if I get a volume in milliliters, I'll have to convert it to liters to use this constant. Okay, I'm looking for atmospheres, so I'm choosing this, or I chose this. I got my moles, and K stands for temperature in Kelvin. And just like the combined gas law we want to use with the ideal gas law, we always need to use the Kelvin scale with this. So 35 degrees Celsius, I add 273, and it becomes 308 Kelvin. Now I look at this, and I got PV equals nRT. I isolate P. So V goes into the denominator, and then I just punch in the numbers. Typically, I'll put in the numbers without the units. I do my unit check over here, but I just wanted to show you how the units end up canceling out. So I take my 0.325 moles, I take my 0.0821 liter atmospheres per mole K, I take my 308 Kelvin, which is my temperature, and then I put my volume 4.08 liters on the bottom. And notice moles cancels with moles, K cancels with K, and this liters cancels with this liters. And I'm left with a pressure in atmospheres. So now I know that it's 2.01 atmospheres, which would be twice normal atmospheric pressure for this gas in this situation. Okay. Now notice it was hydrogen gas, but would that work the same for any gas? Yes, according to the ideal gas law, because all gases behave the same because we don't really think of those intermolecular attractions, okay, essentially between the gases. All right, I think this will help with page 11, and then you can try page 12, look at the key as needed. Thanks for watching.